we just learned about how we can think of our sine and cosine functions as sort of algebraic type functions, or in this case, transcendental functions. But so we can think of them in the same way. So we have a function where y is a function of x. Y depends on x, and so we can talk about domain and range. We can talk about x and y intercepts, asymptotes. Where's the function increasing and decreasing? So all stuff like that. Okay. And so one of the things that you should have learned about in your pre-calc algebra class is this idea of transformations. Okay. So the common transformations that you would have learned and that we're going to continue using would be you could have a vertical shift or a vertical stretch or compression. You could have a horizontal shift or a horizontal stretch or compression. And then you can have a reflection over either the x-axis or the y-axis. Okay, so those are, remember, hopefully you remember those transformations. And so in this graph here, I just want us to look at the sine function. Okay, so the general or the sort of the standard sine function equation has the form y equals a times the sine of k times the quantity x minus b, and then plus c on the outside. Okay. Hopefully you can kind of remember what those constants do to the graph. What does the a, the k, the b, and the c do? How they affect the graph. And you may have seen them with different letters. The actual letters you don't use doesn't matter. It's what's important is where those letters are located. Okay. So just kind of a quick review. The a is a multiple in the front of the function. So you should remember, hopefully, from your pre-calculus algebra class, that a impacts the function with a vertical stretch or compression. Okay, and so we want to see, is that going to still be true here for our sine? Same thing for cosine, but we'll just look at sine for now. So if a is a vertical stretch or compression, then k, which is multiplication inside, it is a horizontal stretch or compression. B, so the x minus b, that is a horizontal shift. And remember, the stuff inside does the opposite. So x minus 3 moves it to the right. But again, we want to see, does that still work? And then the plus c on the outside, hopefully you remember that is a vertical shift. Okay. So let's just look at these four constants and see if they do impact the graph, affect the shape of the graph in the same way that it did quadratic functions and polynomials and exponential and all the other functions you learned about in pre-calculus. Again, we have the general function at the bottom, and I also have the values plugged in there. So right now, the a value is a 1, the k value is a 1, and then the b and the c are both 0. And so really that just is what we see right now is just y equals sine of x. Okay, the ones and the zeros we don't really need to write, so it's just y equals sine of x. So let's start with a and see what that does. Again, normally we should think that a is going to cause the graph to get taller or shorter. It's a vertical stretch. So is that still the case? It sure looks like it, right? So as I increase the value of a, we're seeing the graph get taller, both above the x-axis and below the x-axis. It's getting taller, it's stretching it. I can tell that it's not stretching it or affecting it horizontally because it's still hitting the x-axis. Its x-intercepts are at the same place. They have not changed, only the height of the graph. Okay. So in this case, let's bump it down to a equals 2. Notice that the height of the graph from the x-axis is twice as tall in both up and down as what it used to be. So if the original value was a 1, it's doubled up to now 2. If it was a -1, it's down to a -2. Okay, so we're just making it twice as tall. If that value gets less than 1, right, it's going to become shorter. So if it's 0.5, it's going to be half instead of 1, and it's going to be a -0.5 instead of a -1. And so we call this vertical stretch or compression. When we talk about trig functions, we refer to it as an amplitude. So the amplitude is changing the height, the how tall this wave form is. Okay, so that's our amplitude. And the other thing, if you remember, hopefully, is if A becomes negative, what happens? If A is negative, it's going to reflect the graph. Okay. And so now instead of it going up above the x-axis, everywhere it was above the x-axis, it's now below the x-axis and vice versa. Okay. So the A value is our amplitude. If it's negative, it has a reflection over the x-axis. If it has a value between 0 and 1 or 0 and -1, it is going to be a compression. And if it's bigger than 1 or -1, then it's going to be a stretch. Okay, so that is our A value. Let's look at B next. So for B, in our formula, we have x minus b. So remember, x minus b should shift to the right a distance of b, whatever b is. So if b is a 1, right, that means the graph should take the original graph and move it to the right 1 unit. Okay. Or if it's 2, if b is 2, then that means we have x minus 2 in our parentheses. So y equals sine of x minus 2. The graph has been shifted to the right. Okay. Now, because of the periodic nature of our graph, it's actually possible for it to shift if it shifts just right. So in this case, if it shifts just the distance of pi to the right, it actually looks like it's a reflection over the x-axis. And if we shifted the distance of 2 pi, well, it actually it becomes a copy of the original graph. We're just shifted it to the right, but because it's periodic, it looks the same. Okay, and I can do that to the left. I can shift everything to the left. So if the b value is negative, so what happens if you have minus a negative? It becomes plus. So x plus 4 is a shift to the left. Okay, but again, it can if it shifts enough, it would look like it's the same, right? If we shifted it to the left by 2 pi or about 6.3, then it looks like it's the same graph. Okay, so the b value is that horizontal shift. When we talk about our trig functions, we're going to refer to that value as a phase shift. Okay, and we talked about it in phase. There's a lot that goes into that we're not going to really dig into, but it's related to how far this graph is because of its periodic nature. How far is it away from being its original graph? Okay, so it's in phase with itself. Okay, the next piece we want to look at. Let's do C. So it's the plus constant on the outside of the function. Hopefully, if you remember this, the C value here is just a vertical shift, which we still see that. Okay. In terms of our trig functions, though, this C value also has an special extra role here. If C is equal to 0, then that means the graph is centered on the x-axis, right? So right now, if I have y equals sine of x, and there's a plus 0 on the end, we're not moving it up or down, then the graph is centered on the x-axis. So it's 1 unit. So the top of the graph is 1 unit above the x-axis, and the bottom of the graph is 1 unit below the x-axis. Well, if I change the graph, if I move it upwards, the middle of the graph also goes up. So in this case, if I have a plus 1, so y equals sine of x plus 1, then that's taken the entire graph and moved it up 1 unit. That means it's also taken the middle of the graph where the x-axis was, and it's moved that up 1 unit as well. Okay, so now the middle of the graph is not the x-axis, it's y equals 1. So we're going to call that the midline. So in this case, the midline is the equation y equals 1. That's the center of the graph. Okay, and to figure out the top and the bottom of the graph, remember the amplitude. So the amplitude is the distance from the middle of the graph to the top and the middle of the graph to the bottom. So if my midline is at 1 and the amplitude is a 1, well, 1 plus 1 is 2. So the top of the graph is 2 and then 1 minus 1 is 0. So the bottom of the graph is going to be 0. Okay. So what happens if we change the amplitude? Let's make the amplitude 2. So we've taken the graph, centered at the x-axis, and we've done a +1 for the vertical shift. So now the midline is at 1, and the amplitude is a 2. So from y equals 1, we're going to go, because of the amplitude being 2, we're going to go from y equals 1 up 2 units to 3. So the top of the graph is at 3. And to get to the bottom, we're going to go from 1, the midline, down 2 units. So from 1 down to -1. So the amplitude and the vertical shift kind of help us figure out where's the middle of the graph, where's the top, and where's the bottom. Okay. And so that's kind of how we can think of the amplitude and the vertical shift together. Again, think of that vertical shift as the midline. Okay. All right. The last thing we need to look at is the value of k. And again, just from our knowledge, what we remember of our pre-calculus, the k value should affect the horizontal stretch or compression of the graph. Okay. And since it's on the inside, just like the b value, we do the opposite. So if k is bigger than 1, we should expect the graph to get shorter. And if k is less than 1, we should expect it to get bigger. So if k gets bigger, notice how the graph is getting shorter or narrower. It looks like it's getting squeezed closer. We're seeing more fluctuation, more up and down. So we're going through that wave faster. And it can go really, really fast. Okay. And if we went the other direction, so if we made k less than 1, notice it's pulling that, it's stretching that graph out further and further. So it's going to take more time, more distance to travel through the entire wave. Okay. And for the most part, we're not going to worry about negative k values. So it's always going to have a positive k value. Okay. So what does that k value tell us? It is that vertical stretch, or sorry, that horizontal stretch or compression. So what would happen if k were 2, for example? Okay. So go back to k equals 1. What is the length of the sine period? The normal length, the standard length of sine period. The graph starts at 0. It goes up to 1, down through the x-axis to -1, and then back to the x-axis at 2, or at 2 pi. So remember that the sine graph has a standard period from 0 to 2 pi, a length of 2 pi. If I change k, that's going to change from 0 to 2 pi. It's not going to be 0 to 2 pi anymore. If k is 2, what does that do to the length of a period? Well, if we start at the origin again, we can go up to 1, down to -1, and back to the x-axis. But this time we hit the x-axis at pi, not 2 pi. Okay. So that means if k is 2, the period is half the length it used to be. Which means if you wanted to travel from 0 to 2 pi, you could go through the period twice. Okay. So what happens if k was 3? This one might not be as easy to see, but if k is 3, the period starts here at 0. We go up, down to -1, and back to the x-axis. And I don't have that point marked there, but it's going to be at 2 pi over 3. If we go up and down, back to the x-axis again, up and down, back to the x-axis again, that's the third time we've gone through that cycle, we land at 2 pi. So if k is 3, we can actually get 3 full periods of the graph, 3 full cycles between 0 and 2 pi. Okay. And if we did 4, this one's a little easier to see. If k is 4, now 2 pi divided by 4, so 2 pi is the whole thing, divided by 4 becomes pi over 2. And if you look, if you start at 0, you go up to 1, down to -1, and it ends at pi over 2. And we can get 4 of those loops, 4 of those cycles between 0 and 2 pi. Okay. So it's kind of a cool way that it compresses the graph. So what would happen? You can't see this on the graph, but what would happen? How long would the period be if k was a half? Okay. We can't actually see the whole thing just the way my graph is set up here, but the top half of the graph starts at 0, goes up to 1, back down to 0 at 2 pi. which means it has to go through the bottom half of the graph from 2 pi to 4 pi. So if k is a half, that means the graph is now twice as long as it used to be. Okay, so it's a horizontal stretch. Okay, so hopefully that kind of makes sense. The a value again is our amplitude, and it affects the vertical stretch or compression, and it also affects the reflection over the x-axis. K is our horizontal stretch or compression, and it changes the period of the graph. It's not the period, so that's one thing to make sure you keep track of. K is not the period, but it changes the period. It affects the period. Okay. B is our phase shift. That's what we call it for trig functions. It's our phase shift, but it just changes the horizontal shift, the left and right. And then C is related to our midline, and that affects the vertical shift up and down.